these mean? So the first one, sine of negative theta equals negative sine of theta. Okay? Now, a number example is not a proof by any means. We talked about that last time. But if you want to wrap your head around what's happening, sometimes a number helps. So think about what they're saying. They're saying the sine of negative 30 degrees is the same thing as the opposite of the sine of positive 30 degrees. Okay? For cosine, they're saying it doesn't quite work that way. They're saying the cosine of negative 30 degrees is the same as the cosine of positive 30 degrees. And for tangents, they're saying that it works similarly to the sine, that the tangent of negative 30 degrees would be the same as the negative tangent of 30 degrees. Okay? So take like a couple minutes in your group and decide why you think these were in the calc teacher to just make decisions about what I could give you. So the sum and difference formulas are formulas that we're going to use, but they don't come up as often in pre-calc and in calculus. So these are ones that when you take your test on this and on your final, I would provide these formulas for you on the board. Okay? We're going to prove one of them. Okay? It's kind of a long and daunting task, so we'll see that. Okay, so it looks a little bit confusing here because it kind of is. Okay? So this angle right here is the angle they are calling alpha. So that's the little Greek letter A that's called alpha. Okay? This angle right here is being called beta. Okay? We're just marking some different units on the circle. And that means that this angle right here, from this line to this line, is alpha minus beta. Okay? Because if this angle was 60, and then this one was 20, I would know the difference was 40 because I would take 60 and take out the 20 degree part. Okay? So that part is the part that we're talking about with that subtraction symbol right there. Okay? So this requires us to know some distance formula stuff. Okay? Because what we're going to do is we're going to write the distance from this point to this point. Okay? So, first we have to know the x and y coordinates of the points. Okay? So for this point right here, any idea what our x coordinate would be? So first of all, what's the angle that ends right here at this point? Alpha, beta, or alpha minus beta? Kenny. Okay, alpha is the original angle that we have right here, right? And then remember, we used cosine for x and sine for y. Right? So we would go ahead and we could label that point with cosine alpha and sine alpha. So I'm saying that's angle alpha. I could label the xy pairs cosine and sine. So likewise, what could I label this other point right here that's on the terminal side of angle beta? Michelle? Good. Good. So is everybody okay with our setup first? We named some generic angles. We have angle alpha, angle beta. Based on the fact we use cosine for x and sine for y, we gave them coordinates so it would be written like that. Okay? So the distance formula, if you guys remember this, okay, it's a giant radical, okay? And basically you subtract x coordinates and you square them, and you add it with the difference of y coordinates squared, okay? So we're going to subtract, I want to do it in the right order. So we're going to subtract our x coordinates and square them and add that with our y coordinates squared. Okay? So this is like x1 minus x2 squared and y1 minus y2 squared. Okay? All right. I don't want to deal with the square root, so I'm going to square both sides just to no longer have the square root. So this side would say d squared, but now this side just doesn't have a radical on it anymore. So I have cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. All right, are we okay so far? All right, now what we want to do is we want to multiply out all of that stuff. Okay? So we're going to go ahead and write out what is cosine alpha minus cosine beta squared, what is sine alpha minus sine beta squared. Now when I square this isn't just cosine squared plus cosine squared. Remember, FOIL, okay? So this is cosine squared alpha. Okay. What's the middle term going to be? I'm just thinking about squaring this right now. Think about how you would multiply it out. What's the next term going to be? Negative 2 cosine alpha cosine beta. Because you get two of them when you multiply it out, one and the other, right? And then I would have a cosine beta squared. Then I have the same thing for the sines, right? I'm going to have a sine squared alpha. I'm going to have a minus 2 sine alpha sine beta. And then I'm going to have plus a sine squared beta. Sorry, a little bit of a space issue. So many terms. Now, can we simplify this at all? Is there anything up here, think about the previous identities from the previous days, that we could combine together and simplify it? Which identities did we learn on Friday? Stana? Good. So if you have the same angle and you have cosine squared of the angle plus sine squared of the angle, that's really equal to 1. Do we have that up here somewhere amongst all these terms that we have? So I see a cosine squared alpha. Is there a point where we are adding that with a sine squared alpha? And because addition and subtraction are commutative, we can do them in any order, right? I could change the order so it doesn't matter if it's not right next to it. Kenny? Good. So this sine squared alpha plus this cosine squared alpha are actually adding up to 1. Okay. Is there another place that happens? Jordan? Good. So those two will add together, and they will add up to be another 1. And then I have these other things that don't quite meet that requirement. So then I still have this and this. So it's not that great looking, but it's not as horrible looking as it could be, okay? Because at least I was able to do those things, right? So then here, these two we can just write as 2 if you want. Okay? That'll make it a little bit easier. All right, so now, yes? Like this. All right, so now we're going to do the same distance again, something that should be equal distance, okay, but measure it from a different point. So what were we really finding the distance of right here? We're finding the distance of these 2 points, okay, and notice that connects this angle right here, and what was the name of that angle? Is that alpha, is that beta, or is that alpha minus beta? It's alpha minus beta, okay? So if we thought about this a different way, where I just drew angle alpha minus beta on its own and didn't subtract it from the other 2, okay? This point would be cosine alpha minus beta cosine alpha minus beta. And yes, this is all the work mathematicians go through to prove that things are true. Okay? And if I connected it back down to the axis, okay, or to the 0 degree angle, it would actually be more like this. It would connect back down to this point that would be at 1, 0. So it's basically like if I redrew the alpha minus beta angle so that it started at the initial side, okay, where we always start from 0 degrees, instead of having it be from these two angles, I should have the same distance between points that I have right here as I have right here, because it's the same measurement of an angle, right? We measured the distance of these endpoints for angle alpha minus beta. It should be the same distance as these endpoints when I redraw angle alpha minus beta. So I'm going to rewrite the distance formula again, all that stuff, but this time I'm going to use these coordinates and these coordinates, and then I should be able to set the two things equal to each other because they are different ways to measure equal things, okay? So this would look like, I know. Think about when you, like back in the day, and then you had to prove to somebody that a theorem was true. This is why they have published proofs that are pages and pages and pages long. So we're going to have our same distance formula, okay, square root, but this time our x coordinate is cosine alpha minus beta, and our other x coordinate is 1. Our y coordinate is alpha minus beta, and our other y coordinate is 0. That's a little bit helpful. Okay, not a lot, but a little bit. All right, so again, I would square both sides to no longer have the radical. And I would go through this same procedure that I went through before, writing stuff out in its squared form. Okay, so right here I would get cosine squared of alpha minus beta minus 2 cosine of alpha minus beta plus 1. Okay, so that's just foiling out that first part. The second part is much easier. What is sine of something minus 0? What's anything minus 0? Just what you started with, right? So this is just like having sine of alpha minus beta squared. So at least that part only has one thing. And then just like last time, if we can find a cosine squared of something and a sine squared of the same thing that could be added together, we can call it 1. So that happens here is the cosine squared of an angle plus the sine squared of an angle. So those will make 1. Okay. There was another one right here. And then I have this thing right here. I know. It's a lot. We're almost done. And then you could do it for sine and for tangent. We're just going to do 1. Now you can see why. Okay? All right, so again, why did I write this second distance formula? I can't come up with a new formula unless I can say, hey, here's a way to write this. Here's another way to write this. I'm allowed to set them equal to each other because they're both writing the same thing. And then I can see if a new formula arises for that. So that's what we did with law of sines and law of cosines, right? Here's area for a triangle. Here's another way to write that area for a triangle. It's the same triangle, so they're all equal to each other. Here's this formula that I can now use. So in this case, we said, here's the distance between the 2 points. Here's a different way to write the distance between the 2 points. It's the same 2 points, so I can set them equal to each other. Okay? So I'm going to set this statement equal to this statement. So you guys can do that on your paper. I'm going to write this equals this. I just need to flip the page in order to do it. Okay? Yes? Hold on 1 second. I'll show you where it came from. I'll bring it back up in a second. This one right here. Good? Okay. All right, so I set the two distance statements equal to each other. does it build me any formula? Well, let's see what cancels out and if we're left with something different than what we had before. So I could subtract 2 from both sides, and those would cancel out. And I could divide then by -2 after that. I'll write it out and then my division. Now, if I was a mathematician and I did all this work, and some of them have done this, it takes them like a whole lifetime to prove one thing, okay? So if I'm a mathematician and I do all of this and then I cancel a bunch of stuff out and I just get back something that's like 1 = 1 or something, that doesn't help anybody, okay? So sometimes that happens, but in this case we're going to be good. I'm now going to divide both sides by -2. And what I'm going to have is going to say cosine alpha cosine beta minus sine alpha sine beta equals cosine of alpha minus beta. This is one of the new identities that we're going to be working with. So these are sum and difference formulas. Yes, Brooke?
Why in the final one is it minus the sign?
Oh, it should be plus. Thank you. Sorry. Good job. Good catch. Okay. All right. So this is one of the formulas. This is the cosine difference formula. It's saying if you wanted to find the cosine of the difference between two angles, why would you want to do this? Well, let me ask you guys this. What is the cosine of 15 degrees? Do you know? No. You don't know. You suck. No, I'm just kidding. You don't suck. All right. Can you think of two angles that you do know stuff about, that if you subtracted them, they would give you 15? 30 and 45. So now you guys could find the cosine of 15 degrees because you know 45 degrees and 30 degrees, and you could use those two angles to figure out the other. Does that make sense? So it has a purpose, okay? All right, so there's another formula when this is a plus. There's another formula when this is a sine and a minus and a sine and a plus and a tangent and a minus and a tangent and a plus. But these are all the formulas that will be given to you. So are you ready to write them down? Okay. Oh, you're not even done with this. I'm sorry. These will probably be the only ones. So be happy that you don't have to memorize these ones, okay? All right, so for cosine. Now, there's two formulas. I'm going to write it because I'm lazy. I'm like all the other mathematicians. There's one formula when there's a plus here, and there's a different formula when there's a minus. But the values all stay the same. They just switch those. So I'll explain how it's in a minute. So they both have cosine alpha, cosine beta, and then sine alpha, sine beta. But when it's plus over here, it's minus over here. When it's minus over there, it's plus over here, okay? So the formula for plus means use this one. The formula for minus means use that one. Is that okay? Okay? All right. So then there's formulas for sines and for tangents. These ones will be written on the board for you, okay? For this test and for your final. If you don't like alpha and beta, you can use little a and little b. Yeah. Mm-hmm. And these go, this is like sine of this, cosine of that, sine of that. Mm-hmm. But you don't have to memorize these ones. You just have to be able to use them. You are going to be able to use them. Okay, make sure you copy them down correctly. Yes?
Is sine or cosine the only one where they're opposite?
Yeah, so in cosine, like, it's nice in this way, like it uses both the cosines and then both the sines, but the plus and minus is opposite. In the sine, the addition and subtraction are the same, but it's like evil this way because you have to do like sine of one, cosine of the other, cosine of one, sine of the other. And the tangent, well, there it is. Okay. So remember your goals here. Right. So the next slide has some other formulas technically. Okay. But we're going to come back to this because our last example problem will prove that these are true. Basically, anytime you have to prove these are true, that is a sum or difference. So you just get in or difference. Though these formulas are really complicated, they're not hard to know when to use them. So for example, on like homework 1, and it was like, what do I try? What do I try? What do I try? Right? But with these ones, when you see something with a plus or minus in between it, it's like, what do I try? And it's like the sign of these two things added together. Go try the formula that has the sign of two things added together and see if that helps you make it look different. So at least in this case, it's a little more apparent that that might be a path to travel on, whereas sometimes it's hard to see the other substitutions. They're not as clear. Okay? But we're going to prove how each of these work in a following example. Okay, so we'll do the sine of 105. Cosine of negative 120 would work the same. So we're going to focus on this one because 105 is not usually an angle that we would find the sine of. However, now that we know those sum and difference formulas, if I can think of 105 as a sum or a difference between two angles I do know about, then I can actually find the information that I need. So any ideas of how we could think of 105 as a sum or a difference of any other group of angles? Zach? 45 and 60. So we could think of it as a sum of 45 and 60, and then you would go to your sine angle formula that has a sum, okay? And so when I look at that formula, right, it says do sine of the first angle times cosine of the second angle, add it with cosine of the first angle times the sine of the second angle. And then I just write what I know about each of these. So the sine of 45 is root 2 over 2. The cosine of 60 is 1/2. The cosine of 45 is root 2 over 2. And the sine of 60 is root 3 over 2. Okay? These two things multiplied together are the same as rad 2 over 4. These two things multiplied together are the same as rad 6 over 4. So I have a rad 2 plus a rad 6 in the numerator all over a 4. That's what the sine of 105 is equal to. Okay? So now you can see why we don't memorize it, but that's what it's equal to. Okay? So we can figure it out. So one way that we use these is numerically. If you want to find sine, cosine, or tangent of an angle that you're not familiar with, you see if you can write it as a sum or a difference of two angles that you do know about, and then you just plug into the formula. Okay? All right. These are the formulas that are similar to what you saw on the other side. Okay? So these are like the problems that you guys did in homework 1. But what I was mentioning to you is when I'm doing problems like you guys did in homework 1, oftentimes I sit there staring at it going, what could I try? What should I try? Right? Because there's no like direct, like every time you do this. It's not like that. You have all these different identities and how to substitute them in and out, and you're just hoping that it takes you down the right path to get you to equal this other thing. These are the same exact problems. These are in the same exact category. However, when I look at these problems, on all of them, I would probably start on the left-hand side, because I immediately see something that I have a formula that I can change into something else because of those sums or differences with the angles over there. Okay? So, for example, let's do, which one of these would you guys want to do? I mean, I know if you could only pick one, which one would you want to do? C? Okay. So let's look at C. No, it's not. You're just verifying. You're saying it's true all the time. So it's true for 45, but it actually turns out to be true for others as well. Okay, so if I wanted to verify, remember what we're doing. We're picking one side of the equation, and we're going to use identities and substitute and simplify until we make it look like the other side of the equation. Okay? So let's take sine of theta minus pi over 2. Okay? So I would immediately use my sum and my difference formula. So sine and then two things being subtracted. So look at your formula that you wrote down. For the sine of two things being subtracted, you do the sine of the first thing, cosine of the second thing, minus cosine of the first thing, sine of the second thing. All right? Now, the ones I can calculate, I'm going to go ahead and I'm going to calculate. So like cosine of pi over 2. I should know what that is. Okay? What is the cosine of pi over 2? The cosine at 90 degrees. You guys should know the cosine at 90 and the sine at 90 fairly quickly. Okay, cosine is 0, sine is 1. Okay. 0 times anything? 0. Okay. Oh, it's not supposed to say 1 over secant theta. It's supposed to say negative cosine theta on the other side. We're never going to finish it. This is what. So go up to the printed part of your note guide, cross out the 1 over secant theta, and write negative cosine theta. We're almost done. Like the problem was printed wrong. Fair? Okay? So the problem was printed wrong. So that side should say negative cosine theta. Okay? All right, so we're almost done. So 0 minus cosine theta would be, okay, you guys don't get to do that when you come across a problem that you just can't solve. You don't just get to scratch out the other side and make it that. But I have the edited version. I don't know how the previous one got up there, but this one has it on there. Okay, so it should equal negative cosine theta, and that's it. So here's the deal. These formulas are hard to remember, but you don't have to remember them. You only have to be able to use them. And in my opinion, it's almost a given when you see something like that what your next step should be, right? If it's not written the same way on the other side. You should just substitute it in and solve it, okay? All right. So this is leading where we're going next. Okay. Anybody have any idea? This is a totally different question. Does it ask you to verify this? No. So there's one more set of like identities that we're going to learn to help us in this verifying type of thing. Okay? Yes, set of identities, not one more identity, set of identities. This is what we're doing after we've verified all the identities. We're going to solve equations. Okay? So I'm just throwing it out there right now. Does anybody know an angle that would make this equation true? So sine of something minus pi over 2 equals sine of that same thing. Ashley? Okay, so let's try it. So if we plugged in pi minus pi over 2 is pi over 2. And that side says pi. So it would say sine of pi over 2 equals sine of pi. And those values aren't exactly equal, but it's a nice try. Okay? So you're thinking about all the angles one time around the unit circle. Is there any place where the angle minus 90 is equal to the angle itself? I don't know. Sean? So root 2 over 2 is not an angle. It's a side length. Okay, so let's try 45. So if we plug in 45, we get sine of 45 minus 90, which would be negative 45, equals sine of 45. So does the sine of negative 45 equal the sine of 45? Almost. Yeah, but not quite. Kenny? Okay, so let's try 135. So 135 minus 90 would be 45. And then over here you'd have 135 still. So what's the sine at 45? It's not a hard one. What is the sine of 45 degrees? Root 2 over 2. What is the sine of 135 degrees? Root 2 over 2. Nice job. So 135 is an answer. Is it the only answer? I don't know. We had to stay between 0 and 360. Not be the only one, but maybe on the lower half of the unit circle, right? So this is where we are going. These identities will help us expand that out and look at it in a different way that might simplify it than looking at it through here and have to just keep going trial through error. So we're going to be using these identities in two ways. We're going to keep doing what you did in homework 1. Verify it's true, verify it's true, verify it's true. So these are just more things to substitute in and show that they can make these other things be equal to them. The last way we're going to use it, the last thing we're going to do in this unit is solve equations like this. Okay, for one time around the unit circle and for infinitely many trips around the unit circle. We'll see how that works. Okay. All right, tonight's homework 2.